going to be working with probabilistic embeddings or continuous valued probabilistic unsupervised learning. And the example we're going to be using today to just describe this class of models is going to be topic models, which have been used to model text back in the day. Still, in certain situations, a good way to model text. But what David and I were just chatting about are that text generation, if you want to create text, has advanced a ton past something like a generative model like topic models that we'll talk about today. And GPT from OpenAI is one of these examples of these very fancy text generators. So the thing that I was going to just, and this is just the thing on my mind, it's random, is that I was talking to one of my colleagues who is a psychiatrist about how these engines can do they answer questions about mental health? There's an interest in creating mental health chatbots for people seeking resources and wanting to chat in general. There's some evidence that says that there's at least a subset of population that prefers to seek mental health related help from a machine rather than a person for like a privacy sort of reason. So I'm going to read what happens when he tried this out. So the cue was, when medicines for depression don't work, people should. And there's a pretty standard version of like GPT-2 that various websites have generators for this. And out of that one came, get help to tackle the condition. This includes any conventional mental health treatment. The British Academy of Mental Health stated blah, 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 and it continues. So this feels, fairly reasonable, right, as a response. Actually, surprisingly reasonable, I would say. Remember, these models are trained off a vast amount of just text on the internet and other places.
A lot of text from places like Reddit, even, I believe.
Funny you mentioned that.
Okay.
for the next version. So then he tried this out on another website. And this is a website that is designed for people who want to play RPGs, role-playing games with AIs. But there's a custom part where you can just type in any cue and it responds. So again, same cue. When medicines for depressions don't work, people should be encouraged to suicide. If someone doesn't want to live anymore, let them die. I don't really see what the big deal is. We're just like, oh my, like what just happened here?
Yeah. And there the differences, do you think the training corpora that was used, or is it a different model? Was that GPT-2
so that's the thing. So this is
something
still
else?
GPT-2. What people often do, I asked a friend who does NLP yesterday after we saw this, what did they do to GPT-2 to change the nature of the response in this way? So you can do a little bit of extra training, and also there's a pre-appending that happens to cues on different websites to get different flavors of response that you don't see. So you type in the cue, but the thing that actually goes into GPT-2 is your cue plus something else.
They change the query slightly. Yeah,
that's right. And that's apparently the most common method of personalization, is changing the query slightly. But I thought this was really interesting because we're used to thinking about how AIs might discriminate against particular groups of people, whether by race or gender or age or something like this. And we could imagine setting up an AI checker to check for, biases in this form. But like, how would you imagine setting up a checker where someone is on a random website and decides to ask a mental health question and gets an answer like this one?
You're checking the way that the queries have been personalized or modified in some way to reflect what that website's creator cares about, and we have no transparency.
And it pops up and is totally, because I don't think the creator specifically wanted to give bad mental health advice. But somehow whatever else they did to customize another part of this engine results in
this bad artifact. We need
So,
a warning, buyer beware, do not use this for anything other than this type of query.
right. Yeah, yeah.
This is
I,
this
I
is
think
this is narrow AI. This is like a narrow competency. Only ask me questions that are appropriate for a multiplayer role-playing game. Don't ask me any other questions.
exactly. And this relates to, these notions of like data cards, model cards, this
Yep,
idea of like really transparency about what this model is trained on and what this model is for is just really important, because when we extrapolate past
yep,
the use cases, all sorts of craziness
exactly.
can happen, as we discovered yesterday.
Exactly.
Yeah. All right. So that was hopefully an interesting and fun example for folks. And let us get started with the main topic for today. All right. So today we're going to be talking, as I said, about topic models, just as grounding for where we are. A little while ago, we talked about discrete Z. So this was clustering and mixture models. Last Tuesday, we talked about continuous Z's. We're all in the unsupervised case, so I should maybe write that down. We're in unsupervised learning. And an example of that we gave was PCA. There's many versions of, you could imagine doing this. And today we're going to fill out the very last part of the cube. So today we will finish the cube, and then next time we'll be going on to these bonus areas like structure learning and decision making. And this last part of the cube is, what if we have some continuous hidden variables and we want to think about them probabilistically in terms of how they produce the data or describe structure in the data. Just as reminders, homework 1 is out, and the practical will also be coming out tomorrow. Almost ready. All right, so what we're going to be talking about is what if there is a continuous latent space Z. So this is hidden. And it's going to be producing our variables X. These are the ones that are observed. So our goal is going to be to learn a model from Z to X. And we've already seen this sort of setup when Z was discrete. So this was our mixture model setup, where we believe that the data points were generated from one of some unknown number of potential clusters or mixture components. So Z was the mixture component, and then given which mixture component you were coming from, there was a process to generate the data. Maybe it was something Gaussian. That gave us the Gaussian mixture models. And today, the big difference is that this thing is going to be continuous rather than discrete. All right. So there's many versions or examples of this particular setup. What I'm going to do is I'm going to name a couple of them, and then we're going to spend most of the lecture focused on a specific one that's been used for modeling texts, which are topic models. I'll also just give a warning. Like, I feel like there's certain parts of the course that are tricky for certain reasons. Topic models have a lot of notation. So I'm going to try very hard to keep the notation clear, but definitely please ask questions as this comes up, because the topic models traditionally, every time, there's a lot of indices and notation floating around. All right, so many versions or many examples. So one example is factor analysis. Remember, with generative models, the kind of nice thing is that you just write down your story, right? What is the story by which the data get generated? And so in factor analysis, the story is that every Z comes from some Gaussian distribution, and this is going to be a vector of length k. Right. And then there's a global parameter A, which I'm going to call A, it could be something else, that comes from another Gaussian distribution. And this one is going to be size d by k. I should have maybe listed that before the Zn. And then our Xn is going to be sampled from a Gaussian distribution AZ with some sigma squared noise. So what's happening here is that we're taking the Z, some low dimensional Z, we're multiplying it by a matrix that turns it into a D-dimensional vector, and we're assuming that that's our data. So this is a linear dimensionality reduction. And just the difference between this and PCA is that here we are not making assumptions about any sort of orthogonality or orthonormality of A. We are making some assumptions on what the Z's look like. We're saying that the Z's come from a Gaussian distribution. We have a generative story, whereas PCA didn't have a story associated with it. PCA was just trying to reconstruct or compress the data down as well as possible. Right. So this is factor analysis. And what I want us to note over here is that if we knew Z, then finding A is relatively easy. This is a regression problem, right? Because for every element of X, we're there's a relationship here between Z and X that is just mediated by this linear thing A over here. And if we knew A, then solving for Z is relatively easy. Because again, we're back down to a fairly standard looking regression problem. And I can write out just one of these versions. So like the probability of Z, if you're given X and A, is just going to be proportional to the probability of X given ZA. We have that right here, times the probability of Z by itself. We have that right here. And this is, if these are both Gaussians, which they are in this model, there's just some completing the square that you have to do, or combining, taking products of two Gaussian PDFs. So these tasks on their own are relatively easy, which suggests, an algorithm that alternates between optimizing Z given A and optimizing A given Z. And this is a bit advanced for 181, but what I'm just going to mention here is that there's lots of options here. So we could, for example, take expectations when we try to so when we optimize for Z given A, we could find the expected Z's given A. And then we could find the best A's given Z, and that would give us EM, right? Expectation maximization. We could just find the best Z's and then the best A's, and that would give us like Lloyd's algorithm, like max, right? Find the best cluster, find the best cluster centers. But the important thing that you're noticing, that hopefully we're noticing in unsupervised learning, is that there's a set of variables that are local to each X, and there are a set of global parameters. And oftentimes, the trick to doing inference, because the whole thing is too complicated, is to split up the problem and say that if you knew all the local variables, solving for the global ones is not too bad. And then if you knew all the global variables, the A's, and solving for the Z's is not too bad, and you alternate between the two. So this alternating optimization coordinate ascent is a really, really powerful idea. It comes up in different formats for different particular settings. This is a general theme that I think is useful for us to keep track of. All right, so here's one more, another example. So this was a relatively simple example of factor analysis. A more complicated example is a variational autoencoder, or more expressive example, I should say. And here we have Z again comes from some Gaussian distribution, size K. And then to produce X, X is equal to some nonlinear function of z plus some noise. And now this function over here is characterized, so this is a neural network characterized by theta. So in this particular case, theta, let me just write this down. Theta are the global parameters. So they play the same role in this model as A played in the previous model. So A was the thing that made the Z's into the X's over here in this linear setting. And in the variational autoencoder setting, this theta, which characterizes this neural network, is the thing that takes the Z's and turns it into the X's. And these are the global parameters. Now, this is not as simple to solve, but we have a similar idea. We are like, if we knew the distributions on the Z's, then could we solve for the thetas, right? Like that's similar to doing the EM. And the trick that the variational autoencoder uses, which because things cannot be done in as nice analytical form, is that we learn an inference network so to characterize P of Z given now X and theta, we can't compute this exactly. This thing is now hard to compute. But we say that it can be approximated by some Q phi of Z. And this is a new neural net with parameters phi that give us basically this posterior distribution. So again, going into the details of this is very much out of the scope of something like 181. But what I want to point out here is just kind of how these different things are analogous, that there's always local parameters and global parameters. The common technique is to be able to some way find the expectation over the local parameters and use that to help perform inference over the global parameters. Okay.
Finale, there's a clarification question, I think, about the AZ work with the factor analysis. Just want to check. There's a question about indexing in a third distribution, and I want to make sure that I was able to clear up any confusion there. Okay. Yeah, maybe it was that end there that was causing confusion.
Missing.
Yeah, I think that was the problem for
okay.
Al.
Yes. Yeah. Let me. You know what? Let me change. Let me just change the order in which I'm writing this down to make it maybe also a little cleaner, because I feel like if you're writing it in proper generative, why is my eraser not erasing all of this stuff? Keeps wanting to go back. I think it's trying to be intelligent. Speaking of like AI systems, think that I'm done erasing. All right. So A comes from this normal distribution size D by K. And then for every data point N that you want to produce, we're going to first create a Zn from another normal distribution. And this Z is going to be a vector of size K. And then the X is, I can even, to make it more analogous to the variational autoencoder, I can write this as A Zn plus epsilon, where epsilon is, again, coming from some noise distribution.
Yeah, and is the way to think about this that we generate the A once, and that once we've generated the A, that describes our data?
That's right. So we generate the A once, and then down here with the variational autoencoder, we create the theta once, the big theta one. Yeah, great point. All right. So we've looked at two examples.
Hang on.
Matrix.
I'm sorry, there's just one more clarification. Yeah. Should epsilon have a covariance matrix instead of a scalar?
Yeah, so this is whatever you want to assume. So we can make this, actually, okay, let's make it, let's at least make sure it's a matrix. So sigma squared times the identity. And if you want this to be some more complicated capital sigma, we can do that, but usually people don't. All right. So for our deep dive today into really looking at how these things work, we're going to look at a form of this same form, but a model called topic models. And topic models, as David and I were chatting at the very beginning of class, are models that have been used to model text. And I'm going to give you all first, I'm going to, like, in words, like a bit of intuition about what they do or what they want to do, and then we'll go into like the specifics. So what topic models are saying is that when you have a bunch of text, they're words in the text, and these words can correspond to different topics that are being discussed in the text. So let's say you had a newspaper and you have articles in the newspaper. There might be articles about politics that are likely to have, terms like, government or policy or Biden or these sorts of things. And then there might be articles about health, which, maybe have terms like COVID and vaccine, hospitalization. And then, maybe there's some sports articles, and amongst the sports articles, you have things like team and winnings and quarterfinals or whatever it is. And you can imagine looking at every article and saying that this article has some proportion that's kind of about politics and maybe some proportion that is about health or something like this. But the idea is that every word or that every article consists of a set of topics that it's about, and those topics manifest into the words in the article. That's a high level idea. Now, for text, it's not necessarily the most, it doesn't tell you how to produce the article. It just tells you about words in the article. And so things like the GPT model that we were chatting about at the very beginning, are actually trying to generate actual text, actual words, the sentences, coherent sentences. But topic models, I think, are still very relevant because they're really great for discrete tabular data. So for example, in a lot of the health applications that I work on, we get bags of codes. So we get all the diagnoses that a patient has had. And we can imagine that, let's say there's a patient who has cancer, who has broken their leg. Then their diagnostic codes, they're going to have codes related to their cancer, they're going to have codes related to their broken leg. And so a good way to, and there's no ordering, right? Because it's not text anymore. It's just all the codes that they've gotten in the health system. So something like a topic model makes a lot of sense for that. So just providing a little bit of, understanding of what these topic models are about before we actually present the actual model. All right. So the model itself is going to take the following form. We're going to have a global matrix theta. So I'm going to use theta to be the global parameter. But when I say global parameter, that's the thing that applies to all of the data points, not a specific data points. That's going to be size d by k. And this particular matrix, so let's kind of draw it out here. So it's going to be k, d. If I take a column from this matrix, I'm going to call this the probabilities for topic K. So now, because it's a topic model, each of these hidden things, this k-dimensional thing that I'm squeezing down the space into, is going to be called a topic. Probabilities for topic K of each word D. So let me draw that. So this vector over here, this column vector, is going to be a vector that sums to 1. And it's going to positive values that sum to 1. So it's going to be like a probability vector. And if we were talking about, let's go to the health example. So this is the broken leg topic. Maybe we have a high probability mass on the word cast, and on the word like surgery. But there's like another word out here that's like, I don't know, like zit. There's no probability mass because this is not about allergies or endocrinology or something like this. So you can imagine that each column in this matrix is, again, puts probabilities over what words are likely if this topic is present in the data. So any questions there? I'm going to go through this part a little slowly because this can get a little tricky. All right, no questions. As questions come up, definitely please ask. Now for each document, and now I'm using terms like document, and also I'm choosing parameter names to be consistent with how it is often in topic modeling literature. So I'm using terms like topics and documents, but the document could be, again, like patient record or something like this. Doesn't have to be a literal like news story or something like this. Yes, D is the size of the vocabulary. Why does the column have to sum to 1? So this is a great question. So the key assumption that we're going to make in the topic model is that we have a every time we want a word, we need if we want to generate a new word for this particular document, we're going to have to draw that word from some distribution. But whether things should be normalized or not when you're actually modeling data is a really important question. So let me continue just a little bit further and you'll see why in this particular case we normalize. And then again, we can leave it as an open question as to how you might want to do it in other situations or other alternatives. All right. So for each document, what we're going to be doing is we're going to be drawing a pi n, which is going to be a vector of size k, from a Dirichlet distribution. We will talk about what a Dirichlet distribution is in just a few moments. But this is a process to generate a vector probabilities size k. So the output of this Dirichlet draw is going to be a set of probabilities from 1 out to k. And every time you draw from a Dirichlet, you're going to get another one of these vector draws. And so this pi n corresponds to this is our local hidden variable. So this is, let me just label this here. This is our local hidden. Is our pi n. And then our xn, this is our document, is sampled according to a multinomial theta pi n L, where this is the length of the document. So this is going to be, I call this a document, but let's unpack this a little bit. So what is going to happen, first of all, when we take theta times pi n? Well, theta is, so what we had here is a D by K matrix. This was theta. And then we're going to have a vector of length K, that's pi n. And so when we multiply these together, we're going to get a vector of size D, right? And because pi n is a probability vector and the thetas are all probabilities, right? We're basically taking a convex combination. We're taking a weighted combination of all of these probabilities, all of these topics. So the way to think about this is that, if there was like the broken leg topic that we mentioned, maybe there was the cardiac condition topic over here, maybe there was the cancer topic as rows. Now, whether things will actually be this interpretable is another research question, but we're just trying to make this concrete for us as we're trying to lay this out. So suppose we had these different topics over here. When we multiply by this pi n, we're basically, if this pi n was like 50%, 50%, 0, then it would be like, combine these two, the broken leg and the cardiac disease topic, 50-50, and leave out the cancer one when you create this final vector. So this final vector will also be probabilities on the vocabulary size D, right? So this product over here is giving us the probabilities of each word that are document specific, because we multiplied by this pi n over here, right? So every time we want to generate a new document, we will get a new document specific vector of probabilities of words for that particular document. Now, the L is the length of the document. So how many words do we want to generate for this document? And so the XN here is going to be the counts of each word in the document. And this is going to be a vector of size D because there's D words. And this is just going to be a count of, the word cast showed up 3 times. The word, surgery showed up 5 times in this particular document. So that's the process. And as was asked, why, why this particular process? Like, why not have something that doesn't sum to 1 or do other things? So there's lots of choices here. We're going to go with this because it has particularly nice inference properties. And one can argue, whether it makes sense in various settings or not. Like, one thing that's kind of getting lost here to some extent is the scale, right? Because we're really only doing inference over the proportions, the probabilities of the words, and not the length of the document. So something we struggle with in real life is that, if a patient has like 50 times more codes than another patient, they're probably a lot more sick, right, than the one with fewer codes, unless the person with fewer codes is not interacting with this particular health system. And so there's absolutely cases where this doesn't make sense, but this is often quite useful, surprisingly useful. Like, so to give a bit of context, when we were trying to, for example, make predictions on like sentiment analysis and stuff like this on like Yelp data, movie reviews data, topic models were doing quite well for quite some time and have also been used to analyze structure and data in like industry settings and stuff like this. So there's always a trade-off between the model that seems perfect for your use case and models that you can work with, and topic models often are in that sweet spot. Great. So I promised you, we'll come back to this question of what is a Dirichlet. So let's answer that question now. And that'll finish out our generative story. Right. So we needed a generative process for pi. And previously we were using, this Z, and there is a reason I'm using pi instead of Z, but a new Z will show up. We were having the Z coming from a Gaussian distribution for factor analysis. That was just earlier in this lecture. Z coming from multinomial distribution. That was the mixture model case, the Gaussian mixture model case that we worked on. Now we have something much more complicated. We want the pi to be a vector of probabilities that sum to 1. So what Dirichlet of pi is proportional to pi k, so k equals 1, so big K, alpha little k minus 1. And super early on in the semester, we talked about beta distributions, and the Dirichlet can be thought about as the extension of a beta distribution, just like a binomial turns into a multinomial. A beta can turn into a Dirichlet in terms of the correspondences. And I think the most important thing is that I want to draw a few pictures of what sort of distributions a Dirichlet creates. So now I'm going to draw these pictures, which are going to correspond to the probability simplex. And I don't think we've drawn any of these in class, so let me just explain what I mean by the cartoons. So let's suppose that k, so this is for k equals 3. We can imagine drawing the space of all valid probability distributions over 3 variables as this triangle that says that over here corresponds to put full probability on the one outcome, put full probability on another outcome, put full probability on the last outcome. And then in between, we could imagine, put full probability on, or this particular point corresponds to 50% of the first 2 outcomes, etc. So every point here corresponds to a vector, right? A valid probability vector. And in terms of intuition about Dirichlet distributions, if all the alpha k's are equal to 1, we're going to end up with a uniform distribution over all of the possibilities. So every potential probability vector, or every possible configuration of topics in a document, equally likely. If the alpha k's are bigger than 1, then we're going to end up with a situation where this distribution is peaked around whatever the normalized alpha k's turn out to be. So let's say if all the alpha k's were equal to each other but large, we would end up with a peak kind of in the middle. So it would look like this. That would say that there's a particular set of probability configurations that I think is very likely. Most of the times when you run into an article, the ratio of things that it's talking about always the same. You can imagine like a particular editorial written by a particular person. They always write about the same stuff. So my probability distribution there is highly peaked. And then the last regime that we have, I'm just trying to describe like what our options are the alpha k's less than 1. And in this case, we end up with a U shape that goes kind of in the other direction. So there's peaks at these 3 values out here, and a low region in between. And so this is basically saying that articles are usually about one topic. I have no idea what that topic's going to be, but articles are usually about one topic. And so these are different things that you can express in your probability over what the documents are going to be about. Okay, so I'm going to pause there, take a 2-minute break, because that finishes up our generative story of like how these articles are generated or what a topic model is. And then next we'll go into inference. How do we actually solve this?
There's a quick question finally from Lillian. Maybe just to explain again what the triangle represents.
Yeah. So let me redraw the triangle. So I want to be able to write out, I want to represent all valid probability distributions on k outcomes. In this case, k equals 3. So what are all possible vectors of 3 elements where our kind of constraints are like pi 1, pi 2, pi 3. These don't represent data points anymore. They represent like the specific elements of the vector. That's why it's a little pause, where pi sub k, anyway, referring to this, is greater than or equal to 0, less than or equal to 1, and the sum of all the pi k's is equal to 1. So that's the space that I'm interested in, because I believe that each document has some ratio of different topics in it. And then this triangle is trying to draw like how to draw the space of all these possible things. So again, like you could have a situation with the 1, 0, 0. You could have a situation that's like 1/3, 1/3, 1/3, and that would lie in the middle. Actually, you know what? It's probably even more clear. Let's suppose I had 3 dimensions: pi 1, pi 2, pi 3. But this there's these constraints, right? So what's the space of valid probabilities? Well, I can't just choose something out here. It's not a valid probability. It doesn't necessarily sum to 1. So valid probabilities include putting 1, 1, 1 1, 0, 0, 0, 1, 0, etc. over here. This point would be a valid probability. And if I put dots for everything that was a valid probability, I would get this triangle inside this 3-dimensional space. Does that help in terms of clarifying? And then I'm just drawing this triangle like flat over here. Okay. Justine?
Yeah, I'm really sorry. Following on that, could you just explain the case where the alpha k's are greater than 1?
Yeah, so in the case of the alpha,
what it means, maybe, like, I think I just have some trouble to see, like, concretely what it means for, like, the does it mean that we have one topic which is more likely to be picked for each document?
So if the alpha k's are greater than 1, it means that there's one distribution that is very likely to be picked. So it means that let's say that you are choosing topics for like middle school students, like health concerns or something like this. And maybe that ends up being basically like all middle school students maybe have some trouble with like anxiety and growing up and that whole messy business. And then they, are playing sports and they keep like injuring themselves in sports. And so you don't think there's a lot of variety. You think all the topics are always kind of the same. All the distribution of topics is almost always the same. Or take your favorite commentator. If you're listening to like Stephen Colbert or like John Oliver or something like this, like there's a set of things that they're always talking about, right? Especially 2016 onwards. So their topics in any particular show might be from a very limited distribution. So the alpha k greater than 1 says that I'm pretty sure I know what the range of topics in this document is going to be about. Whereas like the alpha k is less than 1 is saying that I really am not sure, but I think it's about one topic. And there's limitations here. This is, Dirichlet, partly I'm drawing this out to show that Dirichlet distributions can do a few things, but they're not going to be able to do everything. All right, so let's move on. So what we have is we have the generative story up here. And now we're going to move on to inference in terms of how we actually solve these models. So first thing that we have to do is write out our objective. And when we're doing probabilistic methods, our objective is always the log likelihood of the model. So in this case, let's write out some of the specific parts. So probability of x given pi, we now stick the ends in to be specific, and theta is equal to, and we're going to assume that the outcomes come in order. We've done that before as well, just to avoid these extra n choose k permutation terms. So the document is generated, like there's a first word, there's a second word, there's a third word, even though at the end of the day, we're considering counts, right? But that's how it's typically done, and it simplifies that factor. Okay, so for every element, every potential word, so this is a product over D, this is product over words. Which are the dimensions of X, right? The counts were what we had. But what's the probability of a particular word? Well, that is the sum over K pi n K theta KD, right? So how much of that topic is present in this document and how likely is the word given the topic? So this is just writing out the relevant piece of the matrix product up here, right? The relevant this part times this part produces this guy over here. Okay. And so this is a probability of word. How many times did that word happen? It happened xd times. Right. So this is the probability of x given the pi n and the theta. And then the probability of pi n is proportional to, oh, sorry, yes, x and d, thank you. Probability of pi n is given by a product over each element, pi n k, alpha k minus 1. And that was just by the definition of the Dirichlet that I wrote out earlier. And I'm dropping the constant because it's not important for now. All right, so then the probability of x and pi given theta, because these are our two variables and we're assuming theta is some fixed parameter, it's going to be proportional to, well, these things multiplied together. K alpha k minus 1. And this is kind of ugly, right? You know, earlier we were talking about how we might want to, all right, so another question David's putting in is that why are we focused just on the alpha, sorry, what about the alpha, right? What about the theta here? So it oftentimes when we're doing the topic modeling, we think of theta as a global parameter. This is like a matrix of interest. We want to know what are the probabilities of words associated with each topic, and then we're gonna we didn't know that they're going to be about surgery or about broken legs and stuff like this, but we want to know what are the topics that are in this document. So that's of high interest. We're trying to figure that out. And then the alphas are often set as a prior, and just, you know, we assume that they're given. So I can put an alpha here. We are conditioning an alpha, but we're not going to try to optimize. So we're going to, I'll put the alpha there, but I'll note that inference is over just theta and all of these pi n's. We could also do inference over alpha, just makes things a little bit more complicated, but this is going to turn out to be complicated enough as it is. And in particular, if we look at this, this is ugly and it doesn't get better. Like if I condition on pi, this isn't a particularly nice expression to optimize for theta. And if I fix theta, it's not a great expression to optimize for pi, right? So that thing that I was talking about earlier about finding this alternating coordinate ascent, like how do we break up the model so that given one part of the model, the other part is easy, and then we optimize one given the other, and then optimize the other given the one, and we we build up and we improve our quality. Doesn't really just seem possible with this particular setup, right? So we're going to have to make some adjustments. So this is ugly. For inference. So what we're going to do is we're going to introduce, so the approach we're going to take is we're going to be to introduce an auxiliary variable. And I think this is the first time we're seeing this in this course. In 181, we definitely are not going to be expecting you to be able to generate your own auxiliary variables or anything like this. But I think it's a good thing to be exposed to, because it's a neat kind of trick to, again, help break apart complicated problems into easier problems. So the generative model, so there's going to be an equivalent generative model to the model that I gave before. So first of all, we're given theta. So this is a parameter, no prior. If we wanted to have a prior, we could, but we are not for 181 purposes. So given theta, for every document n, the first thing we're going to do is we're going to sample that pi n. What are the ratios of the topics in that particular document? And then once you sample the particular topics, we're going to do another for loop. So for each of the L words, in the document. And the other thing that I'm kind of leaving out at the moment, because I just don't want to deal with it in complexity, is where does the L come from? For now, L is just given because we know the lengths of the documents in real life, right? We know that this document has 100 words in it or something like this. If you wanted this to be a true generative model, what people often do is add like a Poisson or something and say, you know, we generate the pi n, we also generate the L. But for now, let's just leave that out. We're going to sample another local hidden variable, ZNL, from a multinomial given pi n. And this is going to be corresponding to what topic does word L come from? The Lth word in the document, which topic did it come from? Well, you know, the probability of topics in the document is given by pi n. We think all the words are independent. So this is going to be giving us the probability of, or giving us a sample of what word, what topic the Lth word is. And then the word WNL comes from a multinomial distribution. Actually, I should maybe be using categoricals here. Okay, I'm going to cross this out. Categorical is a single draw. Theta, Z, and L. Right, so we're going to pick out, you know, this told us which topic. We're going to pick out that particular topic from our theta matrix. Remember, that's the matrix that tells us what words are associated with each topic, what probabilities. And then finally, and xn is the set of counts of each word. So this is equivalent to the original generative process that I laid out, but we're introducing some new variables. Like we've introduced this Z and L, and we've introduced this W and L. And now instead of thinking of the document as already being compressed into a vector of how many times did each word occur, we're really thinking of the document as first word, flip a coin for the first word, second word, flip a coin for the second word, et cetera, as we go down. And that is going to make our expressions a lot simpler. So how does this help us? So let us write down the probability of X given Z, pi xn, pi n theta. I'm going to put this for the ZNs, the ZNLs out here. Well, now we're explicitly thinking of that length L. So we have to take the product for every word in the document. We need to know its probability. What could that word have been? This is the size of the vocabulary. And what topic could it have come from? And it's theta to the dk. So that's the probability of a particular word and a particular coming from a particular topic times an index. The fact that was the Lth word actually D, and was the Lth, this is all multiplied in the exponent, was the Z topic actually K? Sorry, the Lth topic actually K. So we're sitting at a particular point in the document. We're sitting at we're at location little l, and we have observed that the word at location L is little d, corresponds to the dth word in the vocabulary. And because we're conditioning on Z here, we also happen to know that the word was drawn from this particular topic. And so we have the word, we have the topic, and we're picking out that probability over here. Probability of Z given pi, again, for each of the Z's, we'll have to go over every single Z, and then for every single possible value, we have pi and k indicator that Z and L was equal to topic K, right? Because that's the probability of getting that particular topic, drawing that particular topic for that particular location L. And then we also had the probability of pi n still being proportional to the sum over k pi n k alpha k minus 1. The Dirichlet part has not changed. So this still looks kind of messy, but when we take the products of all of these pieces, so the joint prob is the product of all of these. These terms. What we notice is that it has a lot of things that are being multiplied and a lot of things that are in indicators, like all those summations in particular have gone away, right? Summations have been replaced by our ability to write things down as indicators. And the nice thing about this is that when we take the log of the product of these terms, we're going to get something that's a lot easier to work with in terms of optimization and inference. So let me skip to that just in terms of time. So I'm going to write down the log probability x pi z given theta and alpha. And that's going to be proportional to, because there's always that proportionality bit up here. We're gonna have a lot of terms now. Okay, so I'm gonna write out a bunch of terms, but we're gonna look at them and they're not gonna be too scary at the end. So we have a sum over n for all of our documents. Let me put a big bracket because now this is like the whole data set of all of these pieces. We're gonna, for each document, we're gonna have a sum over k, alpha k minus 1. I'm gonna write this all out and then we're gonna talk about it. Open for me. Okay. Hard to do all of this necessarily at the same time. Okay, so here are terms that end up with things with pi n k. So when I take the log of this pi n k term over here, I have an alpha k minus 1. And when I take a log associated with this pi n k term sitting right here, I have an indicator of z and l equals k, and I have this product over l, which becomes the sum over l over here, all times log of pi n k. Right, so the first, or rather these two terms, the last two terms become this particular term that I'm writing out over here in terms of log probs. And then plus, I still have to take the log of this top term over here. So let me write that guy out. So that's going to be a sum over d, sum over k. And now I'm going to write this as sum over L, indicator W and L is equal to D, indicator that Z and L is equal to K, log theta D K. And I think now we can close the final bracket around the sum over n. Okay. So this is the, yes, indicator is just if the condition is true. So now we've taken this triple product over here and taken the log and we get this term out here. Okay, so that was like, whew, okay, that, big expression. But the really nice thing about this expression is that we can now apply EM. In particular, well, actually, even before we apply EM, let's just take a look at what kind of makes this expression nice. So if we happen to, so the WNLs are observed, right? We know what the document is, right? We're given the X's and we could unroll the X's and we could decide that you are the first word, you are the second word, etc. And we know what the words are. So let's just kind of note down. So this term over here is known, right? This indicator, we know what it is. If we happen to know what these indicators were, right? If we happen to know the Z and Ls, then this optimization, first of all, notice that it splits, right? There is a term that has pi, and there's a term that has theta, and they're not interacting anymore, which is really nice. Because given the Z's, these two are now independent of each other in terms of the optimization. So if I happen to know the Z's, I can solve for this particular top. I can find the pi nk that maximizes this expression pretty easily. I believe we did this in the homework with the generative classification, where you were finding probabilities of particular classes, potentially. I think we did. I'm trying to remember what exactly we did in that homework. But basically what comes out is that the optimal solution to pi nk is to take the alpha k minus 1 plus these indicators if they were observed, and just have your vector be proportional to this term that's out here. I believe we did this with Lagrange multipliers in one of the homeworks. I'm forgetting which exactly it was. And then these are also vectors of probability. So the same idea that, again, from that previous homework, and Lagrange multipliers, you had to take derivatives, also applies. And we can solve for this solution, and the solution is just going to come out to be the Z and L's, the ratio of the Z and L's that actually happened are going to, times the probabilities of the words are going to turn into the thetas over here. So again, if that's going a little bit fast, trust me that if these expressions are given, they're very easy, and you guys did this earlier in term. But we don't know the Z and Ls, right? So here is where the alternating part of the optimization is going to come in. We're going to say if we knew the Z's, we can solve for the pi's and the thetas. And so now we need to think about, if we know the pi's and the thetas, what can we do for the Z's, right? Can we solve for the Z's or optimize this objective with respect to the Z's? So this is the part where we're going to apply EM, and we can take the expectation with respect to Z of this log P of X Z pi given theta term. And again, we're a little short on time, but what we're going to end up with is we're going to end up with something that looks like sum over n, sum over k, k minus 1 plus. And now I have this like thing with far too many indices. We'll talk about it. Log pi k plus sum d, sum over k, sum over L, Q n, L k, still indicator, W n L equals D. Again, that's like something we know, log theta dk. Okay, so here Q and L k is going to be the probability that Z and L equals k, right? That's the expectation over Z that we're taking. So when we do the maximization, these are going to act as partial counts, just as they did in the mixture model case, where in the mixture model case, we made soft assignments. So now you can think of these as partial or soft assignments of topic to this location. And then for for probability of Z given pi and W and theta, that's just proportional to pi n k, this would be pi n, Z n L. Let's make sure I keep track of all of our indices. This is the part that gets confusing for this particular topic. All right, so we can find the probability of Z and L given pi and L, W and L, and theta. That's just the probability, that's just proportional to the probabilities of the word occurring within a particular topic and the base probability of that topic. And so once we have this, so and then this is just, this comes directly from, by the way, like up here where we created the new generative model, right? Remember that the Z's were coming from the theta, sorry, from the pi, and then the W's are being drawn based on the Z's. So these are the two parts that create the Z's. So the prior on the Z is the pi, and the likelihood is coming from the theta. So down here, this is multiplying the prior. This part right here is the prior on Z and L given pi given pi n. And then this part over here is the likelihood term, right? That you also have observed a word. So that gives you information about what the pi was. And so this is going to be giving you this Q and L K. So if we have the pi's and the thetas, and we always have the W's, we can solve for the Z's, the soft assignments of the Z's. And once we have the soft assignments of the Z's, we can go back up here and optimize for the pi's and the, I have this right? NK, sorry. We can optimize for the pi's and the thetas, and then we alternate between the two. So we've got our same EM set up in a much more complicated model than you saw with mixture models. But again, very similar idea. And so if this was a lot, again, the idea that I want people to leave with is that there are ways, a lot of these inference techniques rely on ways to split our models into easy parts. So when the whole thing is difficult, we split it into easy parts. By introducing the Z, we made it such that it was easy to solve for Z given pi and theta. And then it was easy to solve for pi and theta given Z. And this idea doesn't have to be just EM, right? The fact that this property exists means that we could have run, this is again outside the scope of 181, we could have run a sampler, we could have run some other form of optimization to solve that problem. Oh, right. Okay, so I'm also, it's a little maybe hard to read some of these Q and K L's. Yeah, okay, let's make that a little clearer. I'll just make this in the same order as the one down here. Hopefully it's easy enough to read. All right, so cool. I will pause here. Any quick questions? And then we'll go to a concept check, and I'm happy to also hang out a little bit afterwards. If there's any questions. No. All right. Okay, let's move on then to a concept check. So for the concept check, what we're going to be thinking about is we're going to be looking at the just Dirichlet distributions and solidifying our intuition about what Dirichlet distributions actually mean. So let me first paste in the particular link so you all have it in the chat. There we go. And then let us look at the question together. All right, so here's the question that we're looking at. So here we have two different Dirichlet distributions. One is going to have this alpha 1 with 10, 10, 10. So 10s are those weights, the alphas for the so each alpha k is equal to 10. And here the second Dirichlet is alpha, that each k is equal to 0.01. And the first question is basically asking if you see some draws, or the first two questions, if you see some draws, what distribution, which of the two sets of vectors is it likely coming from? Which Dirichlet is it coming from? And actually, we did not really get to this second set of questions. Let me briefly describe it, something you can think about if you'd like to, but it's a little beyond what we talked about. So remember that in the likelihood, or sorry, in the expressions that we found, we had alpha k minus 1 plus stuff, right? Log pi n k, for example. Well, we could interpret that alpha k plus stuff as a new alpha, right? So it stays a Dirichlet, or like things stay Dirichlet distributions. And I believe, again, we talked about this when we talked about with beta distributions very, very early on when we're talking about Bayesian model selection and stuff like this. So you could imagine that when you observe data, so in this case, we've observed class 0, class 0, class 1, class 0, that's the way to read this particular vector. If you observe some data, you have something that corresponds to a new Dirichlet distribution. So what is that posterior? So again, if you feel like you want to think about it a little bit, take a crack, that's great. But I'm noting that we didn't quite get to this in this class, so you may have it from previous lecture. And then, are the draws sparse in either case? Let's make this actually fit. Are the draws sparse in either case? And what I mean is that for these new distributions, for these posteriors, if we're drawing from those posteriors, are we going to get things that look like 0, 1, 0, or 1, 0, 0? That's what I mean by sparse. All right. So why don't folks take, I know we're at time, but why don't folks take just a few minutes to think about these, and then we'll group back.
I opened the rooms.
Okay, cool, thanks. Yeah, it took a little longer.
I didn't do it automatic, so that hopefully it won't send you. It was about to send you again.
Oh yeah, well, it asked me, so I could decline, and then it was fine.
Okay, so I should have done it automatic, and then you could have just declined. Okay. Are any of you?
Oh no, this time no. If you do automatic, it just sends. It doesn't ask you.
They've still got 2 seconds.
Yeah, that's fine. Yeah.
Okay.
Yeah, thank you. Everyone's back. Yep. All right. So I'm going to very quickly go through the solutions to these, and as I was monitoring the responses, it seems like majority of folks are on the right track, which is great. So the first case is Dirichlet with 10, 10, 10. And we were saying how when those numbers are large, you tend to pick the same thing over and over. So that corresponds to the first choice. In particular, 10, 10, 10 is uniform over the different options. So the thing that you're going to pick over and over is the uniform option. Now, alpha 2 is 0.01, 0.01, 0.01. And we talked about how when the alphas are less than 1, you get this kind of U shape that picks out the sparse corners of the simplex. So it's like sure that it's either one topic or the other topic or the other topic, and not a mixture of the two. So we get this third solution right here, or something that would look kind of like this third solution. We're not going to pick out things that put like even mass on different options. Now, when you see data, we're going to basically add these as counts. So we've seen 3 zeros and we've seen 1, 1. Yeah. So we started at 10, 10, 10, but now we've seen 3 more zeros. So it's effectively like we've seen 13 zeros, or 13 of the first choice. And then we've seen 1, 1. So effectively, instead of 10, we've seen 11 of the second choice. And then there's no 2 in this sequence. So we haven't seen any 2s, it still stays at 10. So the first choice here is the correct answer. Again, we didn't really talk about this in class, but hopefully this makes a little bit of sense, something for you all to think about, where once you see the data, those data are real counts, in this case 3 zeros and 1, 1, and we can add them to these Dirichlet, which we can think of as fake counts, just like we thought of the betas as the fake counts very early on in the semester. So by same argument, if we add a vector of 3, 1, 0 to 0.01, 0.01, 0.01, we'll end up with a second choice over here. And in both cases, now we have numbers that are greater than 1 in our vectors. We have this 13, 11, 10. We have this 3, 1, roughly 0. So our draws are no longer going to be sparse. We're not going to prefer to stick to one corner anymore. And I think that's an important note, just because even if this is getting a little more subtle, but even if we think initially that a topic, a document is about one topic, we just don't know which. Once you start seeing counts, the posterior may not be sparse anymore. But again, that's a very subtle point. If that's not completely clear, that's okay. And that's something that can be discussed in office hours or at some later point. All right. So thanks, folks. I'm happy to hang around for a few minutes and answer questions.